so as we started in the last class, we shall see the details of the construction of a function which is continuous everywhere in the real line, but not differentiable at any point. And in order to prove certain things about that, we had started with a preparatory lemma, let us say. So it was okay. Let me say. Okay, suppose f is from AB to R. Okay, suppose f from AB to R is differentiable at sub x in AB, and let us consider two sequences. Let us say that A less than alpha n less than or equal to x less than or equal to beta n, and beta n less than b. That is, we are considering two sequences alpha n and beta n such that limit both of them tend to 0, that is the limit as n tends to infinity of alpha n is equal to x, and similarly limit of as n tends to infinity of beta n is also x. Okay. Then what we want to say is the following: then limit as n tends to infinity of f at beta n minus f at alpha n divided by beta n minus alpha n, this is equal to f prime x. Okay. Now what is the use of this lemma and why we are going through all this? The idea is very simple. Suppose we want to show that a function is not differentiable at some point, then that can be done by constructing two such sequences alpha n and beta n and showing that this limit does not exist. Okay. This limit does not exist. Okay. That is the idea. Okay. So okay, so let us now see how this is proved. Okay, let us it may help to draw some. So see, here you have A, let us say x, and let us say b. So you have alpha n somewhere here and beta n somewhere here. Okay. Let me call this lambda n as beta n minus x divided by beta n minus alpha n. Okay. Then you will see that if you look at 1 minus lambda n, that will be, see, lambda n is this beta n minus x divided by this whole distance beta n minus alpha n. So 1 minus lambda n will be x minus alpha n divided by beta n minus alpha n. Okay. And for lambda n as well as 1 minus lambda n, both lie between 0 and 1. Okay. So 0 less than or equal to lambda n less than or equal to 1, and similarly for 1 minus lambda n. Okay. Now what we observe is the following. Okay. If you look at this ratio f beta n minus f alpha n divided by beta n minus alpha n, we can write it as follows. Okay. We can write it as lambda n into f beta n minus fx divided by beta n minus x. In fact, this is the important step. Okay. And then plus 1 minus lambda n into fx minus f at alpha n divided by x minus alpha n. Okay. Okay. I mean, this is fairly elementary. All that you need to do is put this value of lambda n. See, what is lambda n? lambda n is beta n minus x divided by beta n minus x. So lambda n into this will be, suppose you take lambda n and multiply it to this, what you will get is this f beta n minus fx divided by beta n minus alpha n, right. That will be the value of this lambda n into this, okay, alright. And suppose you multiply 1 minus lambda n is this x minus alpha n divided by beta n minus alpha n. So suppose you multiply 1 minus lambda into this, what you will get is plus fx minus f alpha n divided by beta n minus alpha n, okay, alright. And if you take the sum of this, that will be same as this, okay, okay. So it is a elementary argument, okay. What we can also say further is that I will subtract from both the sides f prime at x, I will subtract at both sides f prime at x. So suppose I write this, so okay, I will make say this minus f prime x is equal to, I can say that lambda n into this minus f prime x plus 1 minus lambda n into this fraction minus f prime x, okay. Do you agree with this? All that I have done is this side I have written minus f prime x and that side I have written lambda n into minus lambda n into f prime x minus 1 minus, that is essentially we are using this fact, okay. F prime x is same as lambda n f prime x plus 1 minus lambda n f prime x. I will subtract this quantity from that side and the other quantity from the right hand side, okay. Okay. And now look at the absolute value, okay. So suppose I take the absolute value here, you can say that that is less than or equal to absolute, this is 0 less than or equal to lambda, so this is same as lambda n multiplied by absolute value of this plus 1 minus lambda n is also a positive quantity, 1 minus lambda n is also a positive quantity, so that multiplied by or at least multiplied by this, okay, alright. Now if you look at the quantities now that are occurring in the bracket, okay, this is f beta n minus fx divided by beta n minus x, we know that as n tends to infinity this goes to 0, so not this goes to, this goes to f prime x, okay. Remember we know this, that is limit as n tends to infinity of f beta n minus fx divided by beta n minus x, because beta n goes to x, as n tends to infinity beta n goes to x, limit of this is f prime x, this is something that we know, okay, alright. And similarly limit as n tends to infinity of fx minus f alpha n divided by x minus alpha n, limit of this is also f prime x, okay, which is same as saying that limit of whatever you have here in the bracket is 0 as n goes to infinity, okay. Similarly limit of this bracket here is 0 as n goes to infinity, okay, alright. But what about this lambda n and 1 minus lambda n? You can say that they are bounded sequences, okay, they are bounded sequences, okay. So you can say that lambda n is less than or equal to n and 1 minus lambda n is also less than or equal to n. So what I can say is that whatever, okay, I will just write here, whatever you have here in this bracket that is less than or equal to, lambda n is less than or equal to 1, okay, lambda n is less than or equal to 1, that is less than or equal to whatever you have here in this bracket, 1 minus lambda n is also less than or equal to 1, okay, right, 1 minus lambda n is also less, so plus the quantity in this bracket, okay, and each of this is going to 0 as n goes to infinity, this also goes to 0 and this also goes to 0 as n goes to infinity, and hence we must have that whatever this quantity also goes to 0 as n goes to infinity, okay, and that is what we wanted to prove, right, that limit as n tends to infinity of this is equal to f prime x, right. Okay. Okay. Now let us come to the main theorem that we, or main theorem, or rather what should say main example. Anyway, let us state in the form of a theorem. Okay, what is the theorem? There exists a function f from R to R such that f is continuous for every x in R, and but f is not differentiable at any x in R. Okay. Now construction of this function, again as I said yesterday, this is something that is contrary to what we intuitively think, that is we cannot imagine such a function easily, okay, and it is not possible to draw a graph of this function. Okay, let us say how one starts the construction. We first construct some auxiliary function, so let me call that function phi. Okay, okay. Let us say define phi from, okay, first I will define it in the interval 0 to 2 to R by phi of x equal to x for 0 less than or equal to x less than or equal to 1, and equal to 2 minus x for 1 less than or equal to x less than or equal to 2. Okay. I think it will help in drawing the graph of this function. Let us, so suppose this is 0 and that is 2, this is 1, then between 0 to 1 it is nothing but x, okay, it is nothing but x, okay, and between 1 to 2 it is 2 minus x, okay, that means it takes the value 1 at 1 and 0 at 2 again, and it is a straight line, so it is this, okay, so fairly straightforward function, okay, it is continuous everywhere, not differentiable here, okay, not differentiable at x equal to 1. Okay. Then what we do is that we extend this function to the whole of R by making it periodic, okay. So we will simply say extend phi to R by assuming this, by phi of x plus 2 is equal to phi x for every x in R. This is such a thing is called a periodic extension, okay. If a function is defined in some interval, okay, you just repeat the values of the function at all other intervals of the same length. For example, just use this formula phi of x plus 2 is equal to phi x, that will say what is the function in the interval 2 to 4, okay. So this extends the function, you are given the function from 0 to 2, this will first extend it from 2 to 4, use the same thing, then you will get function in 4 to 6, 6 to 8, etc., okay, and similarly this side, okay, this will minus 2 to 0, then minus 4 to minus 2, etc., okay, okay, that is what is called periodic extension of the function, okay. But of course this still is not a required function, because you know that this function is continuous everywhere, it is not differentiable at integer points, okay, it is not differentiable at integer points, but what we want is that it should not be differential at any x. Okay. Okay. So now we construct that function and define f from R to R, define f from R to R by as follows. Okay. F of x is equal to sigma n going from 0 to infinity 3 by 4 to the power n and multiplied by phi of 4 to the power n x. Okay. Now this expression has to be exact. Here we can't afford to make any mistakes, otherwise subsequent calculations will all go wrong. Okay. Yeah, fine. This is for each x in R. And now what we want to claim is that this f is the required function. Okay. This f is the required function, that is, this is continuous everywhere but differentiable at no point in R. Okay. All right. Let us first dispose of the question of continuity. Okay. Here you have the function phi of 4 to the power n x. Suppose you call this function as fn. Okay. Suppose you call this function as fn. Fn is phi of 4 to the power n x. Okay. Fn of x is equal to. Is it clear that each of this fn is continuous? Each of this fn is continuous. Okay. Right. Is this a uniformly convergent series? Why is it uniformly convergent? By stress. Look at mod fn x is less than or equal to 3 by 4 to the power n, that is mod fn x is, see, remember again, we are what you are using, the function phi takes the values between 0 and 1. Okay. So each fn x, this is true, 0 less than or equal to fn x less than or equal to 1 for all x in R. Okay. And hence, okay, of course fn x is not the, okay, let us this is 3 by 4 to the power n and into phi 4 to the power n x. Okay. And hence, okay, let us just use this, say this here. Okay. 0 less than or equal to phi x less than or equal to 1 for every x in R. That is clear from here, right? That is clear from here. Okay. And hence mod fn x is less than or equal to 3 by 4 to the power n for every x in R. Okay. Okay. And sigma 3 by 4 to the power n is convergent. Okay. So by Weierstrass M test, okay, the series converges uniformly. Weierstrass M test, the series converges uniformly, and we have said that once the series converges uniformly and if each function occurring is continuous, the sum is also a continuous function. Okay. So we can say since sigma n going from 0 to infinity, this 3 by 4 to the power n phi of 4 to the power n x converges uniformly, remember converges uniformly on R. Okay. Converges uniformly on R. Okay. Okay. To f. Since this happens, f is continuous on R. So remember, in proving all the properties of f, we have to obviously use the properties of phi, because that is how we have started. Okay. F is constructed using phi and other functions which all functions which depend on the starting function phi. Okay. Okay. So we have proved that f is continuous everywhere. We need to show that f is not differentiable at any x, f is not differentiable at any x. So let us take some x in R, okay, and if we want to prove that it is not differentiable at R, we are going to use the technique given by the previous lemma. We will construct two sequences. Suppose I call them alpha m and beta m, because alpha m should be less than or equal to x, beta m should be bigger than or equal to x, both should converge to 0, but f beta m minus f alpha m divided by beta m minus alpha m, that is not a convergent sequence. Suppose we show that, then this will be proved, okay, alright. To do that, let us take some m as some natural number, okay, and look at 4 to the power m x, okay, 4 to the power m x. Now this is some real number, right, this is some real number. So and you know that given any real number, you can always find the integer k such that that real number lies between k and k plus 1, right, that is something you can always do, okay. So we can say that there exists an integer k, that is there exists k in Z such that k is less than or equal to this, less than or equal to k plus 1. Okay, agreed, okay. Now what I will do is that I will take this k by 4 to the power m as alpha m and k plus 1 by 4 to the power m as beta, that is, or which is same as saying that k by 4 to the power m, this is less than or equal to x and this is less than or equal to k plus 1 by 4 to the power m, okay, and I will take this as alpha m. So alpha m is k by 4 to the power m and beta m is k plus 1 by 4 to the power m, okay, okay. Now is it clear that alpha m is less than or equal to x, that is obvious, x is less than or equal to beta m, that is also obvious. What is the other thing that we need to just say? That alpha m converges to x and beta m also converges to x, is that also clear? In fact, if you look at beta m minus alpha m, see if you look at beta m minus alpha m, that is beta m minus alpha m, that is nothing but 1 by 4 to the power m, right, okay, 1 by 4 and that goes to 0, that means what is happening, x is in the, let us say x is in this interval alpha m to beta m and this interval is shrinking and going to 0, okay, the length of this interval is shrinking and going to 0. So alpha m also goes to x and beta m also goes to x, okay. So finally to show that f is not differentiable at x, what we need to show is that f beta m minus f alpha m divided by beta m minus alpha m, that is not a convergent sequence or it does not converge to anything, that will mean that f is not differentiable, okay. That means we have to look at this sequence f beta m minus f alpha m divided by beta m minus alpha m, okay, and we have to show that this sequence is not convergent, okay, this does not converge to anything, and if that is shown, it will mean that f is not differentiable at x. Is that clear? That is the idea, okay. Okay. Now to calculate that, let us first look at the numerator, okay, let us just see what happens to this f beta m minus f alpha m, because as far as beta m minus alpha m is concerned, we already know that is 1 by 4 to the power m, okay, so about that there is nothing much to be calculated, okay, right. Okay. Now this is by definition, now here there is some complications will start, okay, this is sigma n going from 0 to infinity, this 3 by 4 to the power n and phi of 4 to the power n beta m, right, phi of 4 to the power n beta m, okay, phi of, remember, phi of 4 to the power n beta m, okay. And similarly minus f at alpha m will be similarly minus this into phi of 4 to the power n alpha m, okay. So I will just write these things together, minus phi of 4 to the power n alpha m, okay, alright. So now what we have to do after this is that we have to calculate the values of these numbers, phi of 4 to the power n beta m minus phi of 4 to the power n alpha m, okay. Let us just look at those things first, okay, and this will depend on what is n and how n and m are related to each other, okay. What happens if n is less than m, what happens if n is bigger than m, what happens if n is equal to m, etc, okay. It depends on that, okay. So let us just look at those quantities first, okay. Phi of 4 to the power n beta m minus 4 to the power n alpha m, okay, okay. Now, okay, even before going to that, let us just look at this number, whatever 4 to the power n, oh no, not this, it is not this, it is minus phi of 4 to the power n alpha m, right, that is what we require, right, okay, alright. Suppose I look at the number 4 to the power n beta m minus 4 to the power n alpha m, okay, that is same as 4 to the power n into beta m minus alpha m, right, 4 to the power n, and that is, so that is nothing but 4 to the power n into beta m minus alpha m, okay, right, and beta m minus alpha m is nothing but 1 by 4 to the power m, okay, beta m minus alpha is nothing but 1 by 4 to the power m. So I can say that this is same as 4 to the power n minus m, okay. This we can say always, whatever be n and m, we can always say that 4 to the power n beta m minus 4 to the power n alpha m, that will be always equal to 4 to the power n minus m, okay. Now suppose n is bigger than m, okay, suppose n is bigger than m, okay, then this difference is some power of 4, okay, some power of 4, but phi is a periodic function with period 2, okay, okay. So that means phi of 4 to the power n beta m minus this will be 0 if n is bigger than m, that is clear, okay. Remember what is the property of phi, phi of x plus 2 is equal to phi x, okay, phi of x plus 2 is phi x for every x, okay. Similarly phi of x plus 4 is phi x, phi of x plus 6 is phi. So if the difference between the two arguments of phi is a multiple of 2, difference between phi values must be 0, okay. Now consider the case when n is bigger than m, okay. If n is bigger than m, the difference between this number and this number, okay, which is coming here, that is a positive power of 4, positive power of 4, and hence the difference between this must be 0, okay, hence the difference between this must be 0, okay, right. So we can say that this is 0 if n is strictly bigger than m, okay, if n is strictly bigger than m, okay, alright. If n is equal to m, what happens? If n is equal to m, then we can say that okay, let us consider that n equal to m, let us first consider n less than m, okay. If it is n less than m, then it means it is a negative power of 4, okay. If it is a negative power of 4, we can say that between these two numbers, that is again what are the numbers, beta m will be not only just negative power of 4, it is like this, beta m is 4 to the power n beta m is nothing but 4 4 to the power n minus m. So if the difference is the negative power of 4, we can say, moreover we also know that those are not the integers. See, the point is this: if you take any we are looking at the properties of phi, okay, we are looking at the properties of phi. What I want to say is that if n is strictly less than m, if n is strictly less than m, then no integer lies between these two numbers, 4 to the power n beta m and 4 to the power n alpha m. Let us see how this follows. Okay, what will be the 4 to the power n 4 to the power n alpha m? It will be, remember, okay, I think it will be clear if we actually calculate that. Okay, what will be the 4 to the power n alpha m? Alpha m is k by 4 to the power m, so it is k by 4 to the power m into this 4 to the power n. So it is nothing but k into 4 to the power n minus m. Okay, k into 4 to the power n minus m. Okay, and what is similarly 4 to the power n beta m, that will be k plus 1 into 4 to the power n minus m. Okay, where k is some integer, remember k is an integer. Okay, so if n is now let us look at this statement. If n is less than m, then between these two numbers no integer lies. Between these two numbers no integer lies. How does that follow? For example, you just take the case. Let us say n minus m is minus 2. Okay, let us say n minus m is minus 2, and let us say k is let us say 5. Okay, then this will be 5 by 4 and that will be 6 by 4. Okay, that will be 6 by 4. Okay, not 4, 6 by 4 square, that is 5 by, it will something like 5 by 16 and 6 by 16. Okay, that if n minus m is minus 2, we are considering the case when n is less than m. Okay, we are considering the case when, and that similarly for any other integer. Okay, it will be 5 by, suppose k is 5, it will be 5 by some power of 16, and this will be 6 by some, not some power, 5 by some power of 4 and 6 by some power of 4. Between these two numbers there is no integer. Between these two numbers there is no integer. Now what is the significance of this? If between these two numbers there is no integer, that means for example something like this is not possible. This is alpha m and that is beta m, this is not possible. Okay, similarly this is alpha m and that is beta m, that is also not possible. What is possible? That alpha m and beta m both lie either, for example, on this part or on this part. Okay, right. Okay, now which means that alpha m and beta m both are given by, okay, I removed that definition of phi x. Okay, let us again record what was phi x. Phi x was x for and 2 minus x for 1 less than or equal to x less than or equal to 2. Okay, right. Remember, what is the property of phi? One property is that it takes the values between 0 and 1. Okay, it takes the value 1 at all the odd integers. Okay, it takes the value 0 at all the even integers. Okay, and between these integers it takes the value either x or 2 minus x. Okay, so suppose both are either in the interval 0 to 1 or 2 to 3 or 4 to 5, etc., then both will be x. Okay, or if both are in the interval 1 to 2 or 3 to 4 or 5 to 6, etc., in that case both will be 2 minus 6. in that case both will be 2 minus 6. So that means the difference between their phi values will be same as the difference between the two, okay. That is phi of this 4 to the power m beta m minus phi of 4 to the power n alpha m, that will be same as the difference between the two, okay, if n is less than m, okay, that is what we want to say, okay. If so is equal to, I will say that this is equal to 4 to the power n minus m, okay, I will remove this, if n is less than m. Okay. What happens if n is equal to m? If n is equal to m, then again if you look at this, this was okay, let me, it is 4 to the power n minus m, okay, that is 4 to the power 0, okay, 4 to the power 0, okay. And so in that case, see, remember it will mean that alpha m is k and beta m is k plus 1, alpha m is k and beta m is k plus 1, okay, and in that case it will mean that the difference between the two values is just 1, either it is 1 or 2 or 2 or 3, because it is, remember phi is 0 at all odd integers, okay, and it is 1 at all even integers. So between k and k plus 1, one of them will be even and one of them will be, so in that case the difference will be 1, okay. So which is covered by this same formula. If you take n is equal to m, this will be 1, okay, right. So I will say this is if n less than or equal to m, okay. Okay, now we have all the things that are required for what we want to do. So first of all, since, is this clear whatever we have done so far? Of course it is fairly elementary, only thing is you have to be little careful about all these values, and every place we use the properties of this phi, okay. So first thing is that since it is 0 between for n bigger than m, it means that this series will go up to 0 to m, okay, this series will go only up to 0 to m, okay. So this is same as sigma n going from 0 to m, because after for n bigger than m the value is 0, okay, that is what we have seen already, n bigger than m value is 0, and for n less than m value is given by 4 to the power n minus m, okay. So this is nothing but 3 by 4 to the power n and multiplied by 4 to the power n minus m, okay. I think now we have everything that we require. Once we come to this step, everything after this is fairly easy. Now this is just a geometric progression, okay, geometric progression, also finite number of them, so we can easily sum that. Before that we can make one simplification, since here we have 3 by 4 to the power n and here you have 4 to the power n, we can cancel, in fact this we can cancel that, okay, and we can say that this is nothing but and this 4 to the power minus m we can take outside this summation sign, okay, because sum is with respect to n, okay. So we can say this is same as 4 to the power minus m into sigma n going from 0 to m 3 to the power n, right, okay, that is correct, okay. And so this is nothing but geometric series with the common ratio 3, first term is 1, last term is n, so we can easily sum that. So this is nothing but 4 to the power minus m multiplied by, it will be 3 to the power n plus, sorry not n plus 1, m plus 1 minus 1 divided by 3 minus 1, okay, and okay, that is same as, see this is 2, so this is same as 3 to the power m plus 1 minus 1, this divided by 4 to the power m, okay, and 2 into 4 to the power m, that 2 is there, okay. Okay, okay, that is f beta m minus f alpha m, okay, that is f beta m, okay, is this clear? Now what we want is this divided by beta m minus alpha m, but what about beta m minus alpha m? that is nothing but 1 by 4 to the power m, okay. So this is nothing but, and we want to divide by that, so once we divide, this 4 to the power m will cancel, this 4 to the power m will cancel, so we will get f beta m minus f alpha m, that is same as 3 to the power m plus 1 minus 1 divided by 2, okay. Is that clear? Okay. And now all that we need to show is that this sequence is not convergent, this does not converge to anything as m goes to infinity. Is that clear? Okay. In fact, it is not a bounded sequence at all, okay, right. Every convergent sequence should be bounded, but it is easy to see because 3 to the power m plus 1 will explode as for large values of m. So this is not, is unbounded, okay. This is unbounded, okay. So this does not converge to anything, okay. And so what does it mean, that how did we come to all this, that if f were differentiable at x, this sequence should have been convergent and it will converge to the value f prime x, okay. But that does not happen, that means f is not differentiable at x, f is not differentiable at x, and we had taken any arbitrary x in R, okay, okay, alright. So that means f is not differentiable at any real number, okay. So this function f which we have constructed by this fashion, whatever we have written here, okay, okay, that is continuous for all values of x but not differentiable at any x, okay. Is it clear? Okay. Okay. So this was just a construction of a function. All this discussion started with various applications of this uniform convergence, etc. Okay, and I mentioned that we shall also discuss one more theorem, namely the very famous theorem of Weierstrass, which says that if you take a continuous function on a closed and bounded interval, then you can approximate it by polynomials. Okay. In other words, you can find a sequence of polynomials which converges uniformly to that polynomial, okay, to that given function. So that is what is called Weierstrass theorem. Weierstrass theorem, okay. What the theorem says is that suppose you take a continuous function, so let us say that let f on some interval, let f belong to C A B, okay, then you can always find a sequence of polynomials, okay, on A B such that that sequence Pn converges to f uniformly, okay. That sequence Pn converges to f uniformly, okay. We can write the same thing in other words, then we can say that then for every epsilon bigger than 0 there exists a polynomial P such that distance between f and p, that is this d infinity f p, or which we same written as norm of f minus p suffix infinity, or okay, or let us make it even precise, that is same as supremum of mod fx minus px for x in AB. This is less than epsilon. So if you take this epsilon as 1 by n, you can find a corresponding polynomial Pn such that distance between f and Pn is less than 1 by n, and that sequence Pn will converge uniformly to the given function f. That is the idea. Okay. It also, there are various implications of this theorem. One implication is this: suppose you look at the set of all polynomials, okay, it follows from this theorem that that set is dense in CAB. Is that clear? Okay. The set of all polynomials is dense in CAB. Okay. Second thing is, have you heard of what is meant by a separable metric space? What is it? There should exist a countable dense subset. Okay, if a matrix space has a countable dense subset, it is called separable. So using Weierstrass theorem, one can show that CAB is separable. Okay, how does one show that? We have just now we have seen that the set of all polynomials is dense in CAB. Of course, set of all polynomials is not countable. Okay, if you take the, because there are real coefficients and the real numbers themselves are uncountable, so set of all polynomials is not a countable set, but you can take polynomials with rational coefficients. Okay, polynomials with rational coefficients, that will be a countable set. Okay, and that will be dense in the set of all polynomials which is dense in CAB. So that is how one shows that CAB is separable. Okay. Okay, now to look at the proof of this. Okay, first important thing to be discussed here is that we can change this interval AB to any other interval. It doesn't depend on what is the interval, and hence we can as well take the interval AB as the interval 0 to 1. Okay, that is the first observation. So as we say, as we have used this expression earlier, without loss of generality. Okay, without loss of generality, we can assume that this A is equal to 0 and B is equal to 1, or what is same as saying AB is equal to 0 to 1. Of course, let us in order to avoid the triviality, let us take A less than B. Okay, if A is equal to B, then there is just one point in that interval. Okay, and it there is only one, so then the CAB will be same as R, CAB will be same as R, and set of all polynomials also will be same as R. Okay, so that is a trivial case. Okay. Now why we can assume, of course one thing is we can say that these two intervals are homeomorphic. Okay, but of course that does not say why polynomials will be preserved. Okay, so but in this particular case we can give actual homeomorphism. What is that? We can say that okay, either okay, let us say define phi from 0 1 to AB by phi of t. Just take what is called the convex combination of this. Okay, phi of t as 1 minus t times A plus t times B. Okay, call this as x, phi of t is equal to x. Okay, then it is obvious that phi is a continuous function. Okay, and phi is also a bisection. Okay, phi is also a bisection. We can also prove that phi is a homeomorphism. Okay, we can, in fact in this case it is clear, but in even otherwise you should know that if you are given two compact metric spaces, any continuous bisection is a homeomorphism. Okay, but anyway in this case we can also see if since this phi t is equal to x, we can also write t in terms of x. Okay, and what will be that? Okay, this is same as, suppose I want to write t in terms of x, it will be okay, this will be a minus a plus t into b minus a, that is equal to x, right? Or that is same as saying that t is equal to x minus a divided by b minus a. T is equal to x minus a divided by b minus a, and suppose I call this as, let us say, psi x. Okay, so phi is from 0 1 to AB and psi is from AB to 0 1. Okay, phi and psi both are homeomorphism and they are inverses of each other. Okay, phi composed with psi is identity, similarly psi composed with phi is also identity. Okay, all right. Okay, now what is the argument why we can take the interval to be 0 1? We are given a function f on AB. Okay, we are given a function f on AB. If I look at f see, f is a function from AB to R. Okay, f is a function from AB to R. Okay, and phi is a function from 0 1 to AB. Okay, So if I look at f compose with phi, that will be function from 0 1 to r, okay, that is f compose with phi, f compose with phi, that will be a function from 0 1 to r, okay. Okay, that will be a continuous function, right, f compose with phi will be a continuous function, okay. And so suppose we have proved the theorem for the interval 0 to 1, okay, it will mean that for this given epsilon there will exist some polynomial q, let us say q, which is defined on 0 to 1 such that f compose with phi minus q, the distance between that is less than epsilon, that is it will, what it will mean is that there exists q such that supremum of mod f of phi t minus q of t, supremum taken over t in 0 to 1, that is less than epsilon, okay, where the polynomial q is defined on 0 to 1, okay, where polynomial q is defined on 0 to 1. So q is a polynomial, let us say qt is some polynomial, qt is something like say q naught plus q1t etc plus qn t to the power n, and this is defined from 0 1 to r, okay, right. But what we can, let us say we now actually want a polynomial not from 0 1 to r but from ab to r, okay, then what we can do is that you can now consider composition of q with psi, okay, you can now consider composition of q with psi, q composed with psi will be from ab to r, only question is whether q also will be, suppose I call that p as q composed with psi. So what will be that? So p of x will be q naught plus q1 t etc, for t you substitute this, for each t you write x minus a divided by b minus a, for t square it will be x minus a square divided by b minus a square. So suppose you do all those things, it will be a polynomial in x, it will be a polynomial in x, okay, and suppose you go f of phi t is nothing but f of x, okay, phi t is x, and for q of t is nothing but q of t is nothing but p of psi x, q of t is nothing but p of phi x, okay, and so that also will be less than epsilon. So in short you can work out the details yourself. What is to be understood is, given any continuous function on the interval a to b, you can construct a continuous function on the interval 0 to 1 and vice versa, okay, and if the function is a polynomial then the transform function is also a polynomial, and that is why we can straight away start assuming that the given interval is the interval 0 to 1. So it is enough to prove the theorem for that case, okay. Alright, now what is the proof in that case, that we shall see in the next class, okay.